Hello. In this lecture, we will be going over complex conjugates and Demas' theorem. First, we start with a definition of the complex conjugate. For the complex number z is equal to a plus bi, the complex conjugate of z, denoted by z bar, is equal to a minus bi. So basically, we just negate the coefficient of I. So take as an example, z is equal to 3 plus 4i. The complex conjugate of this would be 3 minus 4i. In addition, we have that if you take a complex number z and multiply it by its complex conjugate, we have that this is equal to, if we have z is equal to a plus bi, we have this is equal to a squared plus b squared. Recall that the magnitude of z is equal to the square root of a squared plus b squared. Hence, this is equal to z, the magnitude of z squared. We will go more in depth in a couple slides. Now, we will prove some basic properties involving the complex conjugate. First, we have that the real part of z is equal to z plus the complex conjugate of z divided by 2. So to prove this, let z equal to a plus bi. Then we have z plus z bar over 2 is equal to a plus bi, which is z, plus a minus bi, which is z bar, over 2. Now to add these two complex numbers, we add their real parts and their imaginary parts. We have the real part is a plus a, then our imaginary part is b minus b. This is simply 2a, this is 0. And we have this is 2a over 2, which is a. This is equal to the real part of c, by the definition of a. Now, we'll prove that the imaginary part of z is equal to z minus the complex conjugate of z over 2i. Again, we use z is equal to a plus bi. We have z minus z bar over 2i is equal to a plus bi minus a minus bi, which is the complex conjugate of z, over 2i. This is equal to a minus a plus b minus negative b, which is just a plus b, times I, over 2i. And we have that this part is 0. This part is 2b. Have this is equal to 2bi over 2i. Have this cancels with the 2i in the numerator. Get this is equal to b, which by definition is the imaginary part of c. Next, we will prove the following theorem. Z times the complex conjugate of z is equal to the magnitude of z the whole squared. Again, we take z is equal to a plus bi. We have z times z bar is equal to a plus bi times a minus bi. So to compute this product, we can FOIL this. So we have the first term here is a squared. Then we have an minus abi term. Then we have a plus abi term. Then we have a minus bi whole squared. This is equal to a squared, and Note that these two terms cancel. Then we have a minus bi squared. So we have minus -1 b squared, because I squared is -1. This is a squared plus b squared. And using the fact that the magnitude of z is the square root of a squared plus b squared, we have that this is equal to the magnitude of z squared as desired. Now, if we have that the magnitude of z is equal to 1, we have z times z bar is equal to z squared, the magnitude of z squared. And if we have that the magnitude of z is 1, this right-hand side is just 1 squared, which is 1. And dividing both sides by z, we have that z conjugate is equal to 1 over z. Now we move on to another theorem, that a complex number z is real if and only if z is equal to z bar. So first we need to show that z is real implies z is equal to z bar. Now if z is real, that means the coefficient of I must be 0. Because if it was non-zero, that means z would have some imaginary part to it, which means it's non-real. So you have, if z is real, this is a. So hence we have that z bar is also equal to a, because if we have the conjugate of a plus 0 times I is equal to a minus 0 times I, which is just a. Now we prove the other direction. If z is equal to z bar, then z must be real. So from z is equal to z bar, we have that a plus bi is equal to a minus bi. So we have 0 is equal to, if we subtract a from both sides and take this negative bi over to this side, we have 0 is equal to 2bi, or 0 is equal to bi. This forces b to be 0, so this implies b is equal to 0. Hence, z is equal to a plus 0i, which is equal to a. So z is real. Now we move on to the next set of theorems. Let w equal a plus bi and z equals c plus di. So first we want to show that. So first we'll compute the product w bar times z bar. This is equal to a plus a minus bi times c minus di. Foiling, we have this is equal to ac minus adi minus bci. Then we have a plus from these two negative signs, but then we have a minus from I squared minus bd. So this is equal to ac minus bd minus ad plus bci. Now we will compute wz conjugate. So this is equal to the conjugate of a plus bi times c plus di. Foiling, we get this is equal to ac minus bd plus ad plus bci, the conjugate of this, and this equal to negating the coefficient of I, if this is equal to AC minus BD minus AD plus BCI. And we can see that these two expressions match. The proof for the result regarding division is similar, so we will not go over that. Okay, now we will have a look at this problem. So we want to write 1 over 3 minus 5i in the form a plus bi. To do this, so in general, when you want to convert a fraction like this into the form a plus bi, we multiply by the conjugate of the denominator. So we have a 3 plus 5i and a 3 plus 5i in the numerator. So we have this is equal to, so we have the numerator is 3 plus 5i, and then we have 3 minus 5i. Recall that z times z bar is equal to the magnitude of z squared. So in this case, our magnitude is this is equal to 3 squared plus 5 squared, the whole squared, which is just 9 plus 25, which is 34. Hence we have a 34 in the denominator. And writing this in the desired form, have 3 plus 5i over 34 to, our real part is 3 over 34, and our imaginary part is 5 over 34. So in general, you just want to multiply by the conjugate of the denominator in both the numerator and the denominator. So these properties that we just went over show that introducing complex conjugates can really be useful to simplify complex number expressions. So now we will move on to Demas' theorem. So this theorem tells us that when we raise a complex number to the power n, we get a complex number that's argument is n times what our original complex number was. So Demas' theorem can be proved using induction. So here I will show the 2 case, and from this the n case can easily be seen. So you have this is equal to, so let's call this z. So we have this is z squared, which is equal to z times z. If you recall from the first lecture, when we multiply 2 complex numbers, the resulting argument is the sum of our original complex numbers. So that's why we have an argument of 2 theta. And then our magnitude is the product of the magnitudes of our original numbers. And in this case, we just have magnitude of z is 1. Hence we have this is cosine 2 theta plus I sine 2 theta. So as you can see, this matches up when we put in n is equal to 2. So from Demas' theorem, we also have the following result. We have that the magnitude of a complex number raised to the nth power is equal to the magnitude of that complex number raised to the nth power. We also have that the argument of a complex number raised to the nth power is n times the argument of that complex number. So these are the main results of Demas' theorem. So now we introduce the following equation. We have e to the I theta is equal to cosine theta plus I sine theta. Or, multiplying both sides by r, we have this. In particular, if we set r equal to 1 and theta equal to pi, we have e to the I pi equal to cosine of pi, which is -1, plus I times sine of pi, which is 0. We have e to the I pi is equal to -1. It relates many important quantities in mathematics. So writing complex numbers in this form, r times e to the I theta, our results from Morphs Theorem are trivial. So now we try the following problem. I want to calculate the magnitude and argument of this expression. So first, to calculate the magnitude, let's write c is equal to square root 2 cis pi over 8. So we want to find z to the 20. So the magnitude of z to the 20 will be the magnitude of z, which is square root 2, to the 20th power. And then our argument will be our argument of z, which is pi over 8, times 20. This is equal to square root 2 to the 20 is 2 to the 10. And then we have 20 pi over 8, which is 5 pi over 2. And notice that 5 pi over 2 is greater than 2 pi. Hence, we can take off 2 pi from this angle to get pi over 2. So, our magnitude is 2 to the 10, and our argument is pi over 2. Okay, that ended the lecture. Thanks for listening. We will be posting a part 3 shortly.